Well, here we are at the second part of lecture 4. We're going to talk about an interesting equilibrium constant called Kw and how it relates to the pH scale. So we're going to look at a couple of different calculations here, and you'll have a few opportunities to try a couple of problems that I will try to get posted up on YouTube for their solutions. So in our last part of our lecture, we looked at water and saw that water can behave as either an acid or a base, depending on what exactly it is reacting with. And so that sets up an interesting situation. Because water can act as either an acid or a base, it turns out it can also act as an acid or a base with itself. And we call that process autoionization. So one molecule of water can act as an acid, and another molecule of water can act as a base when two molecules of water collide. And so what we get is an exchange of an H plus between those two water molecules. Now, because it's an equilibrium situation that exists, we can write an equilibrium constant for this reaction. And so we can write Kc. That just means that we have a K written in terms of concentrations. That's all the C means there. Is equal to concentration of H3O plus. And we put the H3O plus on top because it is a product times OH minus. So remember, it's always products over reactants for our equilibrium concentrations. Okay, and they have no exponents because their coefficients are 1. And then I've got two waters here. And so that can become the concentration of water squared. Now you might be questioning some of what I wrote there, because in the last part of the lecture we said that we don't write the concentration for pure liquids in our equilibrium constants. And that's completely correct. We don't. And here we've actually squared it. And so what we're going to do is we're going to take that value of H2O squared, and it just gets moved into the value for the K here. And what we end up with now is our Kc, and we're going to give this a very special name. Again, we're going to give our equilibrium constant here a special label, Kw, W for water. And now it's just equal to the concentration of H3O plus times the concentration of OH minus. This is a very important equilibrium constant, because anytime you have any aqueous solution, anytime you have any sample of water in any kind of chemical reaction, this equilibrium will always hold true, that the concentration of H3O plus times the concentration of OH minus must be equal to that value of Kw. Okay, because it's just water reacting with itself, and so anytime you have water, it's going to react with itself. Let's see how we use this Kw. It does have a constant value. At 25 degrees Celsius, it's equal to 1 times 10 to the minus 14. But like any equilibrium constant, it's only constant as long as the conditions remain constant. That's why a lot of times when you'll see an equilibrium constant, it'll have a specified temperature. So for water, 25 degrees C, basically room temperature, we use 1 times 10 to the minus 14. If the temperature goes up, the Kw will change slightly, and if the Kw goes down, it'll change slightly. But you have to change temperature quite a bit to see an impact. Now, when I say quite a bit, that would mean like change the temperature of the room quite a bit. So if you go to 35 Celsius or 45 Celsius or 15 Celsius, you're going to see a change in that Kw. But if you're working in the lab and the temperature of the room changes by half a degree, the Kw technically changes, but not enough to worry about. So what this means, this Kw, is we know that as water autoionizes, it forms equal amounts of H3O plus and OH minus, because if you make one, you got to make the other. And so their concentrations are exactly the same in pure water. So at 25 degrees Celsius, that means that when I multiply H3O plus times OH minus, I have to get 1 times 10 to the minus 14. And in pure water, those two things have to be the same. So the concentration of both of those values are going to be 1 times 10 to the minus 7. So both of those concentrations will be 1 times 10 to the minus 7. Now, as I mentioned in an earlier slide, in any aqueous solution, the Kw must hold true. In other words, the H3O plus times the OH minus concentrations have to equal the value of Kw, regardless of what that Kw is if you're at a different temperature. Okay, we generally use 25 Celsius. So we're going to assume, unless you're told differently, that the Kw is 1 times 10 to the minus 14. Now, what this means is that if we do something to that solution that increases the value of H3O plus, that means that my concentration of OH minus has to go down. And this is because when I multiply these two things together, they have to be a constant. Okay, and vice versa. As I change one, the other has to change as well in an opposite direction, because when I multiply them together, I still have to maintain a constant value. So, if I have a situation where the hydronium concentration is greater than OH minus, then my solution is acidic. If my hydronium is less than my hydroxide, then we say that the solution is basic. And if the two things are equal, then we say the solution is neutral. Now remember, the only time that those two things are equal really is in pure water. If we have anything else in our solution, then the concentration of H3O plus and OH minus can go out of balance because there's some chemical reactions taking place with some of the things that we added. So let's look at an example here. We want to know, what is the hydroxide ion concentration in a solution that has H3O plus as 3.2 times 10 to the minus 6? Well, we know that the Kw has to equal H3O plus times OH minus. And we know that that value has to equal 1 times 10 to the minus 14. Well, we know our H3O plus concentration, so we plug that in. So we have 1 times 10 to the minus 14 is equal to 3.2 times 10 to the minus 6 times my unknown, my hydroxide concentration. So I take 1 times 10 to the minus 14, I divide by 3.2 times 10 to the minus 6, and I get my hydroxide ion concentration here. And what we end up with is 3.1 times 10 to the minus 9 for my hydroxide ion concentration. Now, the other thing that we could ask is this solution acidic or basic? Well, when we look at our concentrations here, we see we have an H3O plus at 3.2 times 10 to the minus 6. We have an OH concentration of 3.1 times 10 to the minus 9. And so this is greater at 10 to the minus 6. And so my hydronium is greater than my hydroxide. So this solution would be acidic. So here's one for you to try to calculate the concentration of hydronium in a solution that contains 5.5 times 10 minus 5 molar hydroxide. So calculate concentration of H3O plus and then identify the solution as acidic, basic, or neutral. Now, we see these concentrations of hydroxide and hydronium being pretty small in our aqueous solutions, and that's fairly normal. The problem is they can be difficult to work with mathematically. We go way back in history where people had to work with these values, sometimes with a 8th grade education, or something that maybe a 12 or a 13-year-old might be familiar with, because people would leave school early and go to work. And so a gentleman developed a way to express these concentrations in a little bit more convenient way. And we call this the pH scale. Now, what does pH mean? There's lots of chemical urban legends and what it really means. I don't think there's any particular one thing that says, yes, this is what it means. So we just call it the pH scale. Now, pH is a unitless value. So when you say the pH is this, it's not this, then some unit. It's just a number. It has a very simple calculation. We don't have to add or subtract anything. We don't have to manipulate anything. All we have to do is to take the logarithm, the base 10 log of our hydronium concentration, and then we just change the sign. When you take the logarithm of most of our H3O plus concentrations, you'll get a negative value because they have negative exponents. And then that negative sign that's in front of the log tends to change that back into a positive value. Now, when we do a logarithm, we have to take logarithms of things that have no units. You can't take a logarithm of a unit. I say this because I always get this question every year. So for our course, we use concentrations, and that's going to serve our purposes just fine. If you continue on in chemistry and you start getting into higher levels of analytical chemistry and physical chemistry, you'll use things that are called activities, which are thermodynamic ratios of concentrations. So when you have ratios of concentrations, you lose the concentration units and you end up with a unitless value. Those values for activities tend to be very close to concentrations themselves. If you're doing really precise work, it matters. When you're doing first learning about how pH works, it doesn't matter. So we're going to use concentration, and we're going to pretend like the concentration has no units for this calculation. So let's see how this works, because now we have a new way of defining if something is acidic or basic. We saw that we can use concentrations, and now we have a new way of looking at concentrations with our pH scale. So that means that if the hydronium ion is greater than 10 to the minus 7, that solution will be acidic. Now what that means for the pH is that if the pH goes below 7, the solution is also acidic. So it sounds kind of weird. If my hydronium ion concentration goes up, my pH actually goes down. And that's because I have that negative exponent there. So as this negative exponent becomes smaller, so 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, my value is getting bigger. But when I take that logarithm, that means my logarithm would be 6 or 5 or 4, becoming more acidic. So as the pH decreases, the solution becomes more acidic. Conversely, if my hydronium ion concentration is less than 10 to the minus 7, that's going to drive the pH value up. And so pH is going to be greater than 7 if it's less than 10 to the minus 7, and my solution is basic. Sometimes that reverse direction confuses some people. Once you work with it a little bit, it'll become second nature. But as the pH drops, things become more acidic. As the pH goes up, it becomes more basic. And that crossover from acidic to basic happens at a pH of 7. Now, if we have a hydronium ion concentration that is equal to 1 times 10 to the minus 7, then the pH value will be equal to 7, and my solution will be considered neutral. Okay, so that's what I had just mentioned there. So here's a couple of calculations for you to try. We want to know what is the pH of a 0.030 molar HCl solution, hydrochloric acid. One of the things you have to recognize is that HCl is a strong acid, and we talked about what strong acids do and what effect that has on the concentration of the H3O+. And then we have what is the pH of a 0.5 molar NaOH solution. We haven't talked about bases. That's actually coming up. So my slides got a little bit out of order with this problem. But sodium hydroxide is a strong base. It's going to completely dissociate into sodium ions and hydroxide ions. So if you know the concentration of that solution, now you also know the concentration of the hydroxide ion OH-. So give that problem a try. Here's another set to try. The average pH of juice in a lime is 1.9. We want to know what is the hydroxide ion concentration in lime juice. And we'll say it's at 25 Celsius, so we know the Kw there. And we learned that pH is equal to negative log of H3O+, and that means that the inverse function is 10 to the minus. So if we have, let's see here. So we had, log of H3O+ is equal to pH, negative log. Okay, if I change the sign, that gives me log H3O+ is equal to negative pH. And now in order to get rid of that log, I have to use 10 to the. So 10 to the log of something is just equal to that something. And so these are inverse functions that will cancel and leave me with concentration of H3O+ is equal to 10 to the minus pH. All right, both of those should be worked out and on YouTube. I'll be sure to post links in Canvas. If you have any questions on any of the calculations or any of the concepts in this portion of the lecture, please contact me.